Dalton's law of partial pressure have to do with a mixture of gases which do not react. It states that the total pressure exerted by a mixture of gases which do not react is equal to the sum of the component gases which makes up the mixture. Dalton's law of partial pressure states that in a mixture of gases which do not react chemically together, the total pressure exerted by the mixture is the sum of the partial pressure of the individual gases that make up the mixture. That is, mathematically, the total pressure is the sum of the partial pressure of the component gases. That is, Pt is equal to P1 plus P2 plus P3, so on and so forth. It is worth noting that this law is normally used when a gas is collected over water. Let's consider an illustrative example under Dalton's law of partial pressure. A certain mass of hydrogen gas was collected over water at 6 degrees Celsius and 765 millimeter mercury. It has a volume of 30 centimeter cube. Calculate the volume of the dry gas at STP. We are given that the saturated vapor pressure of water at 6 degrees Celsius is 7 millimeter mercury. The options are A, 2.9 centimeter cube, B, 2.93 centimeter cube, C, 29.00 centimeter cube, and D, 29.30 centimeter cube. From the given data, P1 is 765 minus 7 to give 758 mmHg. V1 is 30 centimeter cube, and T1 is 273 plus 6, that is 279 Kelvin. While P2 is 760 mmHg, V2 is what we don't know we are looking for, and T2 is the standard temperature, which is 273 Kelvin. So making use of the ideal gas equation, which says P1 V1 over T1 is equal to P2 V2 over T2. So P1 is 758 multiplied by 30 divided by 279 is equal to P2, that is 760, multiplied by V2, which is not known, and T2 is 273. So let's make V2 the subject of the formula. So V2 is equal to 758 multiplied by 30 multiplied by 273 divided by 760 multiplied by 279. And consequently, V2 on evaluation gives us 29.30 centimeter cube. From the explanation given above, the correct answer is 29.30 centimeter cube, and consequently, the option is D. Let's consider a second illustrative example. A vessel contains 0.3 moles and 1.2 mole of nitrogen and carbon dioxide respectively. If the total pressure due to both gases is 2 atmospheres, calculate the partial pressure in atmosphere due to nitrogen. The options are A, 0.4 atmospheres, B, 0.5 atmosphere, C, 0.6 atmosphere, and D, 0.7 atmosphere. Now, total number of moles of nitrogen and carbon dioxide. (0.3) plus 1.2, that is 1.5. So therefore, partial pressure of nitrogen is number of moles of nitrogen divided by total number of moles times that is, the partial pressure of nitrogen is the number of moles of nitrogen is 0.3, while the total number of moles of nitrogen and carbon dioxide is 1.5, and the total pressure is 2 atmosphere. So when we evaluate this, 3/15 multiplied by 2 over 1, 3 divided by 3 is 1, 3 divided by 15 is 5. That is 2 over 5, which is 0.4 atmosphere. Now from the explanation, the correct solution is 0.4 atmosphere, and consequently the correct option is A. Example 3. A gaseous mixture of 8.0 grams of oxygen and 56.6 grams of nitrogen has a total pressure of 1.8 atmosphere. The partial pressure of oxygen in the mixture is, the options are A, 2.0 atmosphere, B, 1.5 atmospheres, C, 1.0 atmosphere, and D, 2.5 atmosphere. Now solution. Total mass of oxygen and nitrogen is 80 plus 56.6, that is 136.6. Now total pressure assumed by the problem is 1.8 atmosphere. So therefore, partial pressure of oxygen is the mass of oxygen, that is 80, divided by the total mass of oxygen and nitrogen, that is 136.6, multiplied by the total pressure exerted by both gases, 1.8. And this gives us 1.058 atmosphere, which will approximate to 1.0 atmosphere. The partial pressure exerted by oxygen is C, 1.0 atmosphere. Now let's consider the third example. 30 centimeter cube of hydrogen gas was collected over water at 27 degrees Celsius and 780 millimeter mercury. If the vapor pressure of water at 27 degrees Celsius is 10 millimeter mercury, calculate the volume of the gas at 760 millimeter mercury at 7 degrees Celsius. Now the options are A, 288 centimeter cube, B, 280 centimeter cube, C, 284 centimeter cube, and D, 28.40 centimeter cube. Now let's consider the solution. P1 is 780 minus 10, which is 770 mmHg. V1 is 30 centimeter cube, and T1 is 273 plus 27, that is 300 Kelvin. P2 is 760 as given in the problem. V2 is what we expected to look for, and T2 is 273 plus 7, 280. mmHg. So making use of the general gas law that says P1 V1 over T1 is equal to P2 V2 over T2. So P1 is 770 multiplied by 30 divided by 300 is equal to 760 multiplied by V2 divided by 280. So we can now try to make V2 the subject of the formula. V2 is 770 multiplied by 30 multiplied by 280 divided by 760 multiplied by 300. When this is correctly evaluated, it gives you 28.40 centimeter cubed. So this is the correct answer. From the explanation given, the volume is 28.40 centimeter cubed, and consequently the correct option is D. Let's consider the fifth illustrative example. What is the partial pressure of hydrogen gas collected over water at standard atmosphere pressure and 25 degrees Celsius if the saturated vapor pressure of water is 23 millimeter mercury at that temperature? The options are A, 730 millimeters mercury, B, 737 millimeter mercury, C, 73.0 millimeter mercury, and D, 733 millimeter mercury. Let's consider the solution. The standard pressure, which I regard as P total, is 760 millimeters of mercury. Then the pressure of water vapor, as given the problem, is 23 millimeters of mercury. Since the gas is collected over water, the pressure of hydrogen is what we are looking for. Let's give the question mark. And so the total pressure is pressure of hydrogen when it is dry plus pressure of water vapor. And so making the pressure of hydrogen as the subject of the formula, pressure of hydrogen is now the total pressure minus pressure of water vapor. And consequently we have 760 minus 23, giving us 737 millimeters of mercury pressure. Now from the solution on the board, the pressure of hydrogen when it is dry is 737 millimeter mercury pressure. And so from the options, the correct one is B.